Okay, now we're going to go on to slightly more complicated structures. The next group of silicates are called chain silicates or inosilicates, or chain silicates. And they are as you'd expect them to be. They're elongated in one direction. That's normally the c-axis, goes this way of the mineral. And we can write out one of these. There's the c-axis. And here is the silica tetrahedra, like that. The next one on the opposite side of the chain, like that. And the next one farther up, like this. Okay. And if we pick a repeat distance from, say, here to up here, you can count there are two, one silica here, one silica there. So two silicas, to 1, 2, 3, 4, 5, 6 oxygens. So the stoichiometry is 1 to 3 silica to oxygen. An example of this would be pyroxenes, which are the common simple single-chained inosilicates. And enstatite would look like this, MgSiO3. Or if we picked diopside, it would look like this, CaMgSi2O6. Okay. All right, so this is single chain. And now we're going to look at what happens when we have a double chain inosilicates. Again, we're going to do the same thing. We're going to draw this tetrahedral chain like that. There's the next tetrahedron, that, and the next one like that, etc. And now we're going to share this oxygen with another tetrahedral chain over here. Okay, like that. And like so. And this double chain is again elongated along the c-axis in a group of minerals that are called double chain. And the common double chain silicates are amphiboles. Okay, so the repeat distance again would be from here to there. And we can count again, there are 1, 2, 3, 4 silicas, 4 silica. And then there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 oxygens. Okay, so amphiboles that are double chain silicates always have this stoichiometry of 1, 4 to 11. So a common amphibole would be tremolite, which has a formula Ca2Mg5 Si8O22OH twice. Okay? All right. Now we're going to turn to slightly more complicated and linked chains. You can see what's been happening as the number of silica tetrahedra that are linked increases, then the silica to oxygen ratio decreases. Okay, now we're going to look at ring silicates. And ring silicates are quite simple. They look like the same sort of linking. We start with a chain like of tetrahedra here. And then we don't link anything up here or down there, but we link this tetrahedra to one over here, like that, like that. And put in the tetrahedral symbols. This is a 6-membered ring. Virtually all the ring structures in the Earth are 6-membered rings. And it's easy to count the number of silicons here. 6 silicons, so 1, 2, 3, 4, 5, 6, and 6 silicon. And the number of oxygens, there's one that's shared on each of the rings here. There's 6 of those, and then there's 2 more out here. So it's 3 times 6, so there are 18 oxygens. So these would be called ring silicates. And common ones include beryl and tourmaline. And beryl is an example shown here is Al2Be3Si6018. And you can see this has the same 1:3 ratio of silica to oxygen as the inosilicate pyroxene group.